first one is basic, barely, almost neutral. In fact, if you were to call that neutral, you say, yeah, it pretty much is, but the pH is going to definitely be above 7, so it can't be called that, but it's really close. And this right here is acidic. Now, as we fumble around with Kas and Kbs, we have to look at what we call conjugate pairs. Now, we talked about this a little bit before, where acids and bases can be conjugates when they differ by one proton or one hydrogen, according to whichever definition you use it, whether it's Brotherly-Lowry or Arrhenius. Okay? So, what I'm going to do is I'm going to show the relationship between Ka and Kb of an acid-base conjugate pair and see the relationship between them. And I'm going to look at nitrous acid, and this is technically sodium nitrite, but the sodium is a spectator ion, just kind of gets in the way with what I want to do here. So I'm eliminating, when you dissolve this in water, the sodium completely comes off and is not part of this reaction. So we're just going to focus on the NO2 negative here and the HNO2 here. Now, when this dissolves in water, this is a weak acid. And a weak acid slightly dissolves in water to form these two ions, hydrogen ions and nitrite ions. And the Ka expression for that is given as H positive times NO2 negative over the concentration of HNO2. And according to page 727, that is 4.5 times 10 to the negative fifth. We do the same thing again with the nitrite ion, adding water. Well, this is a single displacement reaction. So that means the hydroxide is kicked out by the NO2, and we get HNO2 as a result with hydroxide by itself. Okay, this is -1, this is -1, that allows that to happen over there. So my Kb expression then is OH negative times HNO2 over NO2. We don't include water because that's a liquid. So that's our Kb, and that's our Ka. The question is, what is the value of the Kb? And that's what we're going to find out here. But what we're going to do is that we're going to use something called Hess's law. Now, Hess's law is when two equilibrium reactions are added together, like the two that I've done up here, their K expressions are going to be multiplied. Okay? So, here are the two equations again. Alright, now, when we add two equations together, we cancel out anything that we find on both sides of the equation. So we got NO2 negative on the left and NO2 negative on the right. We have HNO2 on the left and HNO2 on the right. There's nothing else in common. And so this gives us H2O liquid, double arrow, H positive aqueous, plus OH negative aqueous. This looks suspiciously familiar. I wonder what's going to happen. Let's see. Now let's multiply the two expressions together. All right, so we had concentration for the Ka. So the concentration of H positive times the concentration of NO2 negative over the concentration of HNO2. And then we said Kb was equal to the concentration of hydroxide times the concentration of what else we had? Oh yeah, HNO2. And that's going to go over NO2 negative. So Hess's law said, well, go ahead and multiply those two things together. So Ka times Kb equals concentration of hydrogen constant concentration of NO2 negative over the concentration of HNO2 times, and then the Kb gets put over here, OH negative times HNO2 over the concentration of NO2 negative. And we are going to just go crazy here with cancellations here. So HNO2 cancels out HNO2, NO2 negative cancels out NO2, and when the smoke clears, Ka times Kb is equal to the concentration of hydrogen times the concentration of hydroxide. Really? And what's the value of that? Well, that's also known as Kw, which is 1 times 10 to the negative 14. Therefore, dotted triangle, therefore, Ka times Kb equals 1 times 10 to the negative 14. And when we get into problems that are dealing with conjugates, that is going to be an extremely important equation to know. Okay? So, in this particular case, we knew that the Ka is 4.5 times 10 to the negative 5, but we didn't know the Kb. So let's do a little algebra. Plug in 4.5 times 10 to the negative 5th times Kb equals 1 times 10 to the negative 14. Divide by this expression here to get Kb by itself. That cancels out. 4.5 times 10 to the negative 5. Buckle up your calculators, punch in a bunch of numbers, let the smoke clear, and we have 2.22 times 10 to the negative 10. That's a 10, not a 6. And that is the idea behind using conjugate Kas and Kbs. You don't have to regurgitate what I did before that. This is what the final product is that you're going to be using for the last handful of problems. So, let's see how that works. In number 55, it says the Kb for NO2 is what? For HNO2. Well, we just did that problem. We found that the Ka of this was 4.5 times 10 to the negative 5th. Therefore, the Kb for this, we said, is 2.22 times 10 to the negative 10. And if you multiply those two together, you will get, with a little rounding off edging there, 1 times 10 to the negative 14. So let's do this one right here. This is the ion that they gave us, C5H5NH positive. This is a proton or hydrogen more than the base on page 736 called aniline. So we take the Kb for aniline and we find that that is 1.4 times 10 to the negative 5. So now we find the Ka the same way, because Ka times Kb equals 1 times 10 to the negative 14. Plug in this for Kb right here. So Ka times 1.4 times 10 to the negative 5th equals 1 times 10 to the negative 14. Divide both sides by 1.4 times 10 to the negative 5th. And Ka equals 7.14 times 10 to the negative 10. And there's your answer. It's that simple. Oh, if all the problems weren't that easy. Too bad. Let's take a look at the next problem. On page 57. Or problem number 57, page, whatever it is. Same page. How about that? We are given a 0.025 molar solution of sodium propionate. And they want to know what is the Kb of this. Well, we have to find the Ka of its conjugate. So let's, and then they say what is the concentration of propionic acid? Well, guess what? If you replace the Na with an H, that is now a proton more than this base. Remember, the sodium kind of disappears, so we're really looking at C3H5O2 negative with the sodium ion coming off it, but it doesn't really make any difference, but that's where they're getting it from. So this is a base, and it is the conjugate base of this, which is its conjugate acid. And because they are related together like that, we can find the Ka of this, and then use that for my problem here for finding the pH of a base. So we need to find the Ka of this. Go to page 727. This is propionic acid. And if you don't recognize the name, you will find this version, this horrible inorganic chemistry version of propionic acid. We learned it as CH3, CH2, COOH. It's a 3-carbon acid, a common name. Regardless, whatever. But if we look it up in the chart on page 727, we get 1.3 times 10 to the negative fifth. So, you add wall onto this, single displacement, you get the H kicking out the Na, you get H, C3H5O2 negative, and then the hydrogen then is going to be left out. I'm sorry, the OH here is going to be left out. We have it right here. So that's not negative. There's no charge for that acid. It's free! So, yeah, that has a proton added to it, so the negative charge is lost. The OH is now by itself, because the H is combined over here. So that is our equation, our dissolving reaction, if you will, for that. So the Kb is going to be 1 times 10 to the negative 14. Not say equal here. Put an arrow there to show that's the next step. Divided by this 1.3 times 10 to the negative 5. And that is going to be equal to the Kb, which is 7.69 times 10 to the negative 10.